Okay, hey everyone, we're going to do 11.6 now, which is absolute convergence, and then picking up a couple additional tests of the ratio test and the root test. And the ratio test is probably one of the more important tests that you'll actually learn about in this entire chapter. And we can use ratio test and root test to actually show absolute convergence if you need to. So, first definition, let's talk about absolutely convergent. A series is absolutely convergent if the series of absolute values converges. So basically, you don't want it to, say, alternate like we did in the last section. So the alternating harmonic series is convergent, but not convergent, because the alternating harmonic series is convergent, but not convergent absolutely. Sorry, I didn't see the word on that. Confused there for a moment. But yeah, it's not absolutely convergent, because if you take the absolute value of each one, all those negatives go away, and you end up with just a basic harmonic series, which we already talked about diverges. So then we could say, well, the alternating harmonic series might be considered conditionally convergent. So it's conditionally convergent if it is convergent but not absolutely convergent. So the alternating harmonic series converges, but it doesn't converge absolutely. So that would be conditionally convergent. You have to have the condition of it alternating to make it converge. And though there's a theorem at the bottom that says if a series is absolutely convergent, then it is convergent, which just makes sense. If it converges absolutely, then it definitely converges conditionally, and so we just say that it is just overall convergent. If it diverges, then you don't have to check whether it's conditionally convergent versus absolutely convergent, because it'll just diverge. So let's try one. Determine whether the series converges absolutely or conditionally. This, you notice the -1 to the n, that would be like our alternating series from the previous section. And so you make a choice here. Do you want to test absolute convergence first, or do you want to test conditional convergence? And it really doesn't matter which one you do. Let's start with the conditionally convergent part. So that would be your alternating series test, basically. Remember, just like we did in the last section, this is the same thing as -1 to the n times 1 over 5n plus 1. The 1 over 5n plus 1 would be your b sub n, and we would test that. You need the b sub n's, which is in this case the 1 over 5n plus 1. That's got to be bigger than 0, which it would be. On top, you always have the number 1. That's always going to be positive. On the bottom, if you plug in different values of n that are positive, or in this case starting at 0 as well, there's no way to get a negative number on the bottom. So yeah, it's always going to be positive. We need the numbers to be decreasing as we go along. So the next one down the line needs to be smaller than the one before it. So plug a few in if you want to. If I plug in 0, I'll just get 1 divided by 1, which is 1. So hopefully that's bigger than the next one. If I plug in 2, I'll get 5 times 2 is 10 plus 1 is 11. And hopefully that's bigger than the next one. Oh, sorry, I was supposed to plug in 1 first. Oops. That's the deal with plugging, starting at 0 sometimes. I get in my mind that I'm used to plugging in 1, but let's plug in 1 first. That would be 5 times 1 is 6 plus 1 is 7, and then 1 over 11. And so on. So yeah, they are getting smaller. So that's a plus. 3. Not only do they need to be smaller, but we got to find the limit as well. So I would do the limit as n approaches infinity of 1 over 5n plus 1. That indeed does go to 0, because your power on the bottom on the n is bigger than the power on the n on the top, which there are no n on the top. So I would say this series converges, and technically converges conditionally by the alternating series test. So if it was to diverge, for instance, checking the conditional part, then there's no point in checking the absolute part, because if it diverges conditionally, it diverges everywhere. Likewise, if you were to check absolutely first, if you check absolutely and it converges absolutely, there's no point in checking conditionally, because it would be true as well. So absolutely. So then what I would want to do is to do an absolute one. I want to take the absolute value of my series. Now what this will do is, on an absolute value, that -1 to a power would just be 1 every time. And so if I put absolute values on there, I'm really just checking the series 1 over 5n plus 1. And you could try a few different ideas. You could try the test for divergence. You could try a comparison test. That's just a couple off the top of my head right there. And like I said, it doesn't matter which one you do. You could do comparison. You could do limit comparison. You could do, try whichever ones you want to do. I'm going to do limit comparison, just because that's the last one I said. And so if I do a limit comparison test, then I need to compare this series to something I know. So I'm going to compare it to, let's look at 1 over 5n. Now we have a little bit of a problem here in the fact that I can't plug in 0 into that. So what we're going to do is we're going to compensate for that, and we're going to actually start this at 1. This will be 1/5 times the sum from n equals 1 to infinity of 1 over n. This is your harmonic series multiplied by 1/5. And so I know this diverges. Adding those one extra term on the front when n was 0 on the previous series won't do a whole lot to change that. So if I was to do a limit comparison, I would divide the two terms. So I could divide the one I'm comparing it to divided by the original one. So I could do the 1 over n divided by, or if you want to put the 5 down there, it doesn't really matter. Whether you put the 5 in or just the n one. To the 1 over 5n plus 1. And so I get the limit as n goes to infinity of 1 over 5n times 5n plus 1 over 1. This limit would be 5n plus 1 over 5n. As you go to infinity, the powers are the same, so I just get the ratio of the coefficients. And so I can just get 5 over 5, which is 1. You might remember when we did limit comparison, I got 1 every time there too. So not really coincidence. So that's a finite number bigger than 0. That's all you have to have. And so if you have that, then the two series have to do the same thing. So since the 1 over n, or the 1 over 5n, would have diverged, this diverges the original series. The absolute value of that would also diverge. So this implies that this series diverges by the limit comparison. And that's by limit comparison. So hopefully that makes sense. So overall, this series is conditionally convergent. So your actual answer to this would be that it is conditionally convergent. Let's try another one. Same sort of idea. Here we have the summation from n equals 1 to infinity. It looks like a alternating series test again, and that is a good reason why. It is an alternating series test. So you can pull that out front if you want to. You don't have to. That's kind of up to you. So if I was to test my alternating series, this part would be b sub n. And I would need b sub n, which would be 1 over n. I said n and wrote m. Isn't that crazy? N cubed plus 1. That has to always be 0. It is. The top's always 1, so that's going to be positive. The bottom is a number that's positive, cubed plus 1. That's always positive, so that's good. We need the terms to be decreasing. So if you plug in 1, for instance, I get 1/2. Hopefully the next term is smaller. If I plug in 2, I get 8 plus 1 is 9 on the bottom. If I plug in 3, 3 cubed is 27 plus 1 is 28. So yeah, this is definitely getting smaller. And I need the limit as n goes to infinity to be 0. And it would be. Notice there's more n's on the bottom than there are on top. So as you go to infinity, this thing goes to 0. So this thing does converge. And it converges conditionally by the alternating series test. But maybe you want to know if it converges absolutely. Well, then I have to look at a little bit different series. I would take the series and take the absolute value of it. And just like on the last one, the absolute value is going to do nothing but get rid of that negative 1 to a power. Because the negative 1 to a power, it will either be positive 1 or negative 1. Taking the absolute value of that will give me positive 1s. The reason why it doesn't affect the bottom is because n cubed plus 1 is positive for every term from 1 to infinity, no matter what number you plug in. So that's not going to change anything. So now we're going to look at that term. So what would be a good way to test that one? Well, how about we just do basic comparison instead of limit comparison, just to show you a different one. So if I did comparison, I need these terms to be compared to something. So I'm actually going to compare this to, since there's just a 1 added to the bottom, why don't we compare it to 1 over n cubed? That's a p-series that I know converges. This part right here, since your p is 3, which is bigger than 1, this converges. And you might remember we have to compare these things. You have to make sure that your inequality is correct. So looking at your inequality, the one on the right, the 1 over n cubed plus 1, has a bigger denominator because you're adding 1 to it. And so a bigger denominator makes it be an overall smaller fraction. So we're going to have the 1 over n cubed be bigger than the 1 over n cubed plus 1, which is good. That means if the 1 over n cubed converges, it will push the other one down to also converge, which is exactly what we want to do. So since the 1 over n cubed converges and it's bigger, then I know that our sequence or our series n equals 1 to infinity of 1 over n cubed plus 1 also converges. Oh, that looks awful, doesn't it? Converges didn't come out very well. Let's try that again. Also converges. By comparison. Now, we actually showed that it converges Absolutely, because we took the absolute value of the original series. So this right-hand side implies that the series n equals 1 to infinity of -1 to the n over n cubed plus 1 has to converge absolutely. And so had you actually done the right-hand side part first, there would be no reason to do the left-hand side, because if it converges absolutely, it also has to converge conditionally. So you take a chance on which one you want to do. So had we chosen to do absolutely first, then we would have saved ourselves the work from the left-hand side. But it doesn't matter. Likewise, if you went the other way around, if the left-hand side is done first, the conditional part, and it fails, there's no point in doing the right-hand side. Okay, let's talk about some tests. The ratio test is one way we can jump straight to just doing absolute convergence. So the ratio test says if you have a limit going to infinity and you take the absolute value of our sequence inside our series, and we're going to add 1 to the ends and then divide by the original sequence, we want that to come out to a number, and a limit, an L. And if that limit is less than 1, it has to converge absolutely. And so we're not even testing conditional convergence here. We're testing only absolute convergence. Or if I do that same limit and I get a number bigger than 1 or infinity, which would also technically be bigger than 1, then I automatically know the series diverges. And if it diverges, then it doesn't matter if it's conditionally or whatever, it just diverges. And the bad one is, what if it came out to be exactly 1? You find your limit and it's exactly 1. All that tells you is nothing. You don't know if it is convergent or divergent or whatever. You cannot draw any conclusion to that. And so you usually have to pick some other test to see whether it converges or not. And so that's the ratio test. The ratio test, one good thing to look at when you're doing the ratio test, if you ever see a problem in a series that has a factorial on it, then you're probably going to do the ratio test. And you'll see that as we go along. So speaking of to the ratio test, we're going to look at these 3 problems where it says, what can you say about the series on each one of these tests? So they're applying the ratio test here. Notice it's a sub n plus 1 divided by a sub n. And we're going to do the limit as n goes to infinity on each one of these. And so the first one is equal to 8. So on that case, 8 is bigger than 1. And so if you have an 8 or any number that's bigger than 1, this will tell us that this series, that this summation from n equals to 1 to infinity of this a sub n has to diverge by the ratio test. Because it's bigger than 1. Likewise, on part B, since it's 0.8, that's less than 1. So that would say that our series for the sequence a sub n converges by the ratio test. Basically, if you're less than 1, you'll converge. If it's bigger than 1, you will diverge. And then part C, the fact that it's equal to 1, when you're testing and it comes out to be exactly equal to 1, what you can say is absolutely nothing. It is inconclusive, so I could not tell you if that series converges either absolutely or conditionally or diverges. I can't tell you anything about that series if it comes out equal exactly to 1. So let's try one here. Use the ratio test to determine whether this series converges or diverges. And the fact that we're doing the ratio test, I can tell you whether it converges absolutely because of the absolute values that are already on the ratio test. And so if I use the ratio test on this problem, what I want to do is do the limit as n goes to infinity of. I want to take the a sub n. Remember, all of this stuff in here is a sub n. Technically, if you want to take the whole thing, you can, but you do not have to take the negative 1 to the n minus 1 because this right here is sufficient enough. The absolute values would get rid of the negative 1 anyway. And so I'm going to take the 3 to the n divided by the 2 to the n cubed. And then on top of that, I have to add 1 to every n. So I have to do 3 to the n plus 1 over 2 to the n plus 1, and then n plus 1 cubed. Like I said, if you put the negative 1 to the n minus 1 in there, you can, but it'll just go away with the absolute values anyway. And so what I'll do is I'll take the one that's on the bottom and I'll flip it over and multiply it. So I'll have 3 to the n plus 1 over 2 to the n plus 1 times n plus 1 cubed times 2 to the n cubed over 3 to the n. And so you have to do a little bit of remembering about how exponents work. Like for instance, you have a 3 to the n on the bottom right that will combine together with the 3 to the n plus 1 on the top left. Like bases, so you subtract your powers. So if I subtract them, n plus 1 minus n, this will cancel into this one to just leave a 3. And likewise, you can do the same thing with the 2's. 2 to the n will cancel with the 2 to the n plus 1, subtracting the powers. I'll have a 2 left over. So since the absolute value of 3 and the absolute value of 2 is still 3 and 2, you could actually pull the 3 and the 2 out in front of the limit because there's no n on those numbers anyway now. And so it has no bearing on the rest of the problem. So I'll have an n cubed on top, and I have a n plus 1 cubed on the bottom. So hopefully that's okay. Notice now that the powers on the top and the bottom are the same. They are both n cubed. And if your powers are the same on top and bottom as your n is going to infinity, your answer is the ratio of the coefficients in front. So in this case, what's in front of these n's is already positive. There's a positive 1 in front of the n cubed, and there's a positive 1 in front of the n inside of the parentheses there. So this leaves me with 3 halves times, that limit would say that this goes to 1 over 1 cubed, which is just 1 anyway. So this is 3 halves, which is greater than 1. The ratio test says that if you get a number bigger than 1, the series diverges by the ratio test. And that would be your answer there. So hopefully that one wasn't too bad. Let's try another one. Alright, use the ratio test to determine whether it converges or diverges. Notice this one has a factorial on it. So like I said earlier, if you ever see one with a factorial on any series, it's probably a good guess that you want to do a ratio test to determine that with a factorial. And so I will have the limit as n goes to infinity. Notice also here, I don't have negative 1 to a power. I have negative 3 to a power. And so that negative 3 to a power, I'm going to actually use that inside my ratio test. If it was negative 1 to a power, that would just be 1, and multiplying by 1 doesn't change anything. But multiplying by 3 will. And so in the denominator, I'll have negative 3 to the n minus 1 over 2n plus 1 factorial. In the numerator, I'm going to add 1 to everything. So on the top, I'll have negative 3 to the n, and that's it. Because if you add 1 to n minus 1, the 1's cancel to give you just an n. And on the denominator, if I replace the n, I'll have 2 times n plus 1 factorial. And so my little absolute value bars are a little bit too short. So I'm going to, just like on the last one, flip the 1 on the bottom over and multiply it. So I'll have negative 3 to the n. And this is now going to be 2n plus 3 factorial, because it's 2n plus 2 plus 1, times, I'll have a 2n plus 1 factorial over negative 3 to the n minus 1. Now, like on the last one, you have the like base of negative 3, and if I subtract my powers, then I can combine those together. So I'll have a n minus the n minus 1. And so these two will cancel to give me just a negative 3 left over on top. Because it's an absolute value, you could go ahead and just factor out that 3 if you wanted to. So I'll have a 3 times the limit as n goes to infinity. And then I want to combine these factorials together. So on top, all I'm left with now is a 2. Oh, my 2 didn't show up. Kind of came out a little weird there. So let me erase that part. I'll have a 2n plus 1 factorial. On the bottom, 2n plus 3, I have to work my way back down to make it match 2n plus 1. So I'm going to rewrite this as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And that might look a little weird, and you may not remember all the details about that. Just keep in mind, this is no different than if I had a 6 factorial on top, and I had a, say, a 4 factorial on the bottom. I could rewrite that as 6 times 5 times 4 factorial, so that my 4 factorials would cancel, and say 6 times 5 is 30. I'm just doing that with the letter n instead of numbers, so that now the 2n plus 1 factorials will cancel. So this becomes a 3 times the limit as n goes to infinity of 1 over 2n plus 3 times 2n plus 2. Now, as you're going to infinity, these absolute values actually don't matter at this point because we're plugging in positive values for n. Positive numbers added with a 3 or a 2 are still going to be positive. So the absolute values you could probably drop off at this point if you wanted to. But as you're going to infinity, there's more n's on the bottom than there are on top. So that limit will eventually go to 0, which is less than 1. The fact that it comes out to be less than 1 says that this original series converges. In fact, it converges absolutely. It's an absolute convergence by ratio test. So hopefully that's not too bad. To go along with the ratio test, there's another test that we want to talk about as well. So that other test is called the root test. The stipulations are almost identical to the ratio test. You have to have a limit. You have an absolute value on the sequence. If it comes out to be less than 1, it converges absolutely. If it's greater than 1 or if it comes out to infinity, it diverges. And if it's equal to 1, it is not going to tell you anything. It is inconclusive. You're not dividing anything here, though. It's not an a sub n on the bottom and an a sub n plus 1 on the top. Instead, you're going to take a root, and you're going to take the root to get rid of whatever power happens to be on the sequence. And so if we get rid of that, then hopefully we can come up with a pretty easy way to find the whether it converges or diverges. So let's try one. Use the root test to determine whether this series converges or diverges. So you'll notice there's a n for a power on the entire thing. That's a great giveaway that you'll want to do the root test. And so I would do the limit as n goes to infinity. And we're going to do the root to match with the power. So if it was an n squared or n 2n or something like that, we would do that root. So we're going to do the nth root of, and it's an absolute value, so we're going to do the absolute value of n squared plus 1 over 2n squared plus 1 to the nth power. And we pick that nth root to match with the nth power so that the root will cancel the power off for us. And we're left with the limit as n approaches infinity of just n squared plus 1 over 2n squared plus 1. And technically you're still in absolute values. Now at this point the absolute values are not necessary because you're squaring numbers and adding numbers to it, so you're going to be positive no matter what, starting with n equals 1. So at this point what we'll notice is that the squared matches on top and the bottom. So there's a 2 on top and there's a 2 on the bottom. If your powers match, you're looking at the ratio of the coefficients in front. That would be a 1 over a 2, which is less than 1. As long as you're less than 1, that series converges by the root test. And it's as simple as that. And again, that's converging absolutely. Okay, we'll try one more. Now in this case, we have an n squared for the power. So you could take an nth root here and come up with something that looks a lot like what's in that box on the left-hand side. One of the definitions for your exponential Euler's number that you saw in Cal 2 is that it's the limit as n goes to infinity of 1 plus 1 over n all raised to the n power. So if you've never noticed that rule before, there's about 3 or 4 different definitions for the exponential e number. So that's just one of them. So I'm going to use that little fact on this one because my series that I'm working with looks a lot like this definition. The only difference is this is an n squared in our problem versus an n. But I can fix that because I could take the nth root of 1 plus 1 over n to the n squared power. Now, in this case, you might remember that when you have a power underneath the radical, you're actually going to end up with dividing the n squared by the n, which is called your index, if you remember that term from radicals. The nth root, the n is your index. And so when you divide them, you actually end up with the limit as n approaches infinity of 1 plus 1 over n to the n power. That is my definition up here on the top. The absolute values, again, don't matter at this point because you're plugging in only positive numbers for n, and so we would only end up with positive numbers anyway. And so we get the definition for E. This is E, which is greater than 1. E is about 2.71828, and blah, 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 blah. So we get something bigger than 1, which means our series diverges by the root test. And that's pretty simple. At least I think so. So the ratio test is probably going to be more important to you than the root test, especially in the upcoming sections when we start doing power series. So if the root test is not looking too exciting, don't worry about it too much. It's just another option to do, but we're really going to focus in on the ratio test when we pick up in the next few sections.